Thank you, Greg, for the introduction. I'm Xiang Ren. I'm a PhD student from the computer science department at USC. So today I want to talk to you about how to turn massive text corpora into machine-readable or machine-actionable structures in a way that demands very light human efforts. And please just interrupt me for questions during the talk. So turning data into knowledge is one of the most intriguing challenges in the big data age. And we have already seen great success in mining knowledge from data that are structured, things like spreadsheets, databases, information networks. But mining knowledge from data that are unstructured, most likely is text data, is a much harder problem. Not to mention that the vast majority of the data that we're collecting today actually is unstructured text data. So the focus of this talk will be talking to you about how to turn this massive amount of unstructured text data into some sort of structures. So what are the structures or the text structures that I want to focus on? Let me give you an example here. This is a piece of review about a New York City hotel and its text. So when people read it, they will first try to identify the entity of interest type. Things like hotel is an organization, Broadway shows is event, Junior's Cheesecake is a restaurant. And then they will start by bridging up these entities of different kinds by the relationships of different types. Things like hotel is close to Broadway shows and it's located near the Times Squares. So the type entities and the type relationships all together form the structures or the structural facts of this piece of review about a hotel. And why we are so interested in such kind of text structures, because once we dig out these structures, they can be critical for us to applying different sort of data mining and machine learning techniques that used to work really well on structured data now can be just easily applied on top of these text structures to really understand the text corpus. I want to give you a concrete example here by showing how a real product is using these kind of text structures. So TripAdvisor engineers, they want to find out interesting collections of hotels. What does that mean? That means hotels that actually sharing the nearby attractions, similar kinds of restaurants nearby, and then they have very similar facilities. And this will give insights into a particular city. So what I do is I run my algorithms to detect different sort of entities from the hotel reviews, like the attractions, the facility, different attributes of the hotels, and then the restaurants near them. And then they use these different sort of entities as the features in a clustering algorithm, and then group those hotels together to provide this interesting collection of hotels. So they found out many interesting collections for New York City hotels. Things like Catcher Show, basically a hotel that actually are pretty close to those Broadway shows, and then near the High Line is the hotel along the area of the High Line attraction. And that was just an example on showing how our real life product is using these text features in their sort of downstream application. But it's also getting this such structure is also very beneficial for our sciences. For example, for life science, if you can dig out such structures from those PubMed papers. So what is happening here is that the UCLA Medical School researcher and also Mayo Clinic doctors, they want to have find out the distinctively related entities for a particular type of disease, let's say a particular type of heart disease. So what I do is they run my algorithm to detect different biomedical entities from the PubMed papers, including the abstracts, the paper contents for those, let's say, disease, drugs, genes, proteins, pathways, and also they use my algorithm to detect different sort of relationships between these biomedical entities, including how the disease gene are associated, how the drug is targeting different kinds of genes. So then they can, using these entities and relations extract from text, analyzing how they are co-occurring in the massive amount of the life science papers, mostly is the PubMed papers, to figure out what is the, let's say, what is the genes that are distinctly associated with the cardiomyopathy, a particular kind of heart disease. And by doing so, they can design a system that answers questions like what proteins are distinctively associated with cardiomyopathy. So that was just two examples on showing how this text structure could be very beneficial for both our sciences and our real-life products. And the algorithms I designed actually has been transferred to different institutes and companies like Microsoft, Bing. They're using these entity detection techniques to find out product information from the act's description, and the US Army Research Lab using this to detect terrorist attack-related information from web forums posts of different languages. And they need to use such automatic technique because there's no way they can find out a bunch of experts to manually annotate this entity information and their relationships from the vast amounts of the text data of different kinds and of different languages from different domains. And if we can find out the right kinds of text data to get such text structures, there will be tons of exciting applications to solve the present problems in our sciences and the society. So your personal intelligent assistant could be even more smarter if they can access to the document that related to your professions or your work. And the online education system could be more personalized if they can access to the student-generated content, I mean the text structures extracted from those student-generated content. And moreover, by analyzing the right kind of text data, you can build up more powerful data analytics systems for healthcare. You can help the computational social sciences, and you can build up better downstream application to facilitate the decision-making process. But the key question happens here is that whether we can have a general technique that works for any kind of corpus, I mean corpus written in different genres, and it's covering topics from different domains, and it's written in different languages. And you also need a technique that actually demands very light human effort because you don't want to repeating to find out those experts. But when we look back in the prior work that natural language processing, so what I do is actually adopting a process that is very manual effort extensive. What does that mean? So what I do is they usually, if they have a corpus at hand, they want to get these structures, I mean the entities of different types and relationship of different types. The first step they do is they find out a bunch of domain experts for that particular corpus. And then they sample a subset of documents from that corpus, ask these domain experts to label for the structures, like the entity names, the entity types, the relationships between these entities. And then they use this label data as the training data to build up extraction rules or particular kinds of machine learning models. And this model and extraction rule works really well for this particular corpus. But things is, once they switch from this corpus to the other corpus of different natures, things like from news articles to biomedical papers to customer reviews to legal documents, you need to repeat this process all over again. And that means for this new corpus, you need to find out a new bunch of experts that knows really well about the contents there, and then do the annotation, do the model building, and do the extraction process. So you can tell such a process is actually slow and costly, and most importantly, if the structures that you are concerned with get to be more and more complex, let's say over 1,000 different entity types and relation types, even a human may make mistakes because this subjective judging process. So how do you really get a technique that can work for different kind of corpus and then try not to including more human errors in this process? That's the key challenge. And my work, yes.
Are you comparing also to OpenAI, or is your work OpenAI?
Great, that's a good question. So Pedro just asked a question about whether my techniques is comparing to open information extraction, things like Washington UW's OpenAI system. And the answer is no, because the concrete setting that I'm focusing on in this research is that the types we're interested in and the relation types we're interested in are actually given by the domain experts, or it's confined to a certain type schema. So we call that closed information extraction. Versus OpenAI is actually that they don't have any idea about the types they are focusing on, and they want to explore these types. Yes. So my work, the Effort-Light StructMine, actually still using human knowledge. So I mean, we are still leveraging the knowledge in our work, but we are leveraging those human knowledge in a way that demands very light manual efforts. And what does that mean? That means we are actually taking advantage of those freely available structured facts that are storing in the external knowledge bases, and we try to leverage them to automatically generate label data for the corpus that we're doing at hand, and use those maybe noisy label data for the corpus to build up corpus-specific models, and those models will work really well for extracting structures for this particular corpus. And I call this method Effort-Light StructMine. It means that the goal of my work is actually to turn the text corpus into structure, or in other words, mine the structure for this unstructured text corpus. And Effort-Light means we are actually trying to propose a method that actually very nice human offers, but taking advantage of the knowledge base freely available structured facts. And by doing so, we can enable very quick downstream application development for different sorts of corpus, and most importantly, we can avoid those human errors once we try to dive into very complex structure mining tasks. And putting this method in a bigger picture, it falls under the category of the distantly supervised learning systems. And this kind of system is actually a lightest one in terms of the human effort compared to other manual system or learning system, including the handcrafted systems, the supervised learning system, and the weakly supervised learning system. So the handcrafted system trying to ask human to not only label the sentences for the structure, but also need to design the templates for those rules that you are going to extract, versus supervised learning system trying to reduce this template engineering effort by just asking human to put out the examples on a sentence and then build up machine learning model, versus the weakly supervised learning system further want to reduce this human effort, and then they say domain expert don't need to annotate every single token in a sentence. They just need to give us a set of names for that particular entity, or a set of entity pairs for that particular relationship, and then they can use those as the seeds to find out more structures of the same kinds. Finally, the distance supervised learning system, let's say they say human don't need to even involve into this manually annotation process, and those kind of examples can come from freely available structures stored in the external knowledge bases. So since the foundation of distance supervision is the external knowledge bases, and the good news we found out that is that such kind of knowledge bases is actually so rich. So we can see this kind of knowledge bases is covering different domains. I mean, in each vertical domain, say human common sense knowledge, or the biomedical knowledge, or the art knowledge, they actually have very specialized knowledge bases in each of these vertical domains, and it's getting more and more in terms of the coverage, I mean in terms of the diversity, but also in terms of the coverage. You can see that in the Wikipedia, for example, actually has been very actively enriched and updated by the human crowds in a very impressive speed. So both in terms of the diversity and the coverage, the knowledge bases is actually growing in a very nice cases. So given this good news, why don't we try to think about how we can take advantage of this part and try to get the overlap with this, for this part, between this part and the text corpus we are dealing in hand. And this overlap region actually represents the matchable information between the knowledge bases and the corpus. Things like the entity names, or the entity types, or the relationships of different types. Of course, after this matching, you will find out a vast majority of the corpus actually still unmatchable. And that goes to the next slide that tells you whether we really solve the problem by just this simple distance supervision idea. So you can see distance supervision provides us a mechanism, an automatic mechanism to generate the label data for a particular corpus in a very nice way. But then does this solve all the problem? The answer definitely is no, because at least two challenges left unsolved. The first one, as you can see, we are taking the overlap between these two different sources, and there will be a matchable part in this process. But then we found out that this matchable part actually is very sparse, and the reason is that even the knowledge base is expanding in a very nice speed, but then not all the facts has been captured. And even for those facts not have been captured, even for the facts that already been captured, based on our current techniques, like entity linking techniques, only a small part of them can be matched to the corpus we're dealing at hand. So to just give you an example here, the junior's cheesecake we just seen actually does not have a Wikipedia page dedicated to its knowledge information. For example, what a type junior's cheesecake is, or how it's related to other entity in the knowledge bases. That's not exist in our current knowledge base. And my study across 3 different kinds of corpora, including New York Times Yelp reviews and tweets show that only less than 20% of the corpus actually is matchable to the external knowledge bases. So you can see this part is very small, and the question is, how do you get from this raw matchable part to the vast majority of the unmatchable part to get the whole structure out? So definitely you need to do some sort of expansion to go from matchable part to the unmatchable part, but how do you do this in a very accurate way? Another challenge come out in this process. So you can see even for the matchable part that we already get the label data, the labels may not be very accurate or appropriate. To give an example here, many entities actually are labeled with multiple entity types in our knowledge bases, like United States labeled as both location and government, and that's true in general because human crowds know this is the truth. But then when you place this United States, this entity into a particular sentence or context, you will find out that there will be some sort of mismatch. Like New York City is my favorite city in the United States. Here, it is referred as a location, versus in the other sentence, the United States needs a new strategy to meet this challenge. It's referred as a government. So then, when you assigning all these labels to every single sentence that United States will be mentioned, actually there will be some mismatch. So you're introducing some improper label or false positive label into these different mentions of the United States. So the matchable part, since the labels are not assigned in a perfect way, how do you clean up these noisy labels while you are doing the expansion from the matchable part to the unmatchable part? So that's the second key challenge. In my work, Effort-Light StructMine, trying to take two major ideas to solve these two challenges. Since we see this sparsity of the matchable part, we definitely need some sort of technique to do this expansion from the small matchable part to the large unmatchable part, and that will be done through some kind of contextual bridges, which I will introduce shortly. What does that mean? And since these contextual bridges in the text corpus could be very sparse as well, I mean, people have a variety of ways in mentioning different relationship between the entities. So you need some sort of techniques to consolidate those sparse contextual bridges to make the propagation or the expansion process more effective. That's the first idea. And since we observe many noisy labels in the matchable part, so when you're doing the expansion, you want to clean up this noise and you want to make sure you pick the right label for those unmatchable part as well. So I designed a specialized optimization objective functions to pick the best labels regarding the context. And that's the key idea. And this will be done for both the matchable part in the training stage and for the unmatchable part in the prediction stage. So altogether, I'm going to harness the power of data redundancy, especially the data redundancy for the contextual bridges in a very massive text corpus, and I'm using graph-based joint optimization technique to formalize these two ideas. So putting into a big workflow, the Effort-Light StructMine, with these two ideas in mind, we're going to start with a raw text corpus, and we're going to break the text corpus, the sentences in the corpus, into different chunks. Some chunks representing entity names, the other chunks representing the context unit, which is the context bridges or those different relation phrases that we're going to introduce by the sort of data-driven text segmentation algorithms. And with these entity names, you can then apply distance supervision using these knowledge bases to get those entity names and the pair of the entity names labeled with entity types or relations. And that gives you the matchable part. And here, technically, we call them partially labeled corpus. And using these partially labeled corpus, you can then train corpus-specific models using all sorts of machine learning model that you prefer in mind. And using this machine learning model, applying back to the unmatchable part, you can get the structures for the whole corpus. And I have published over 15 papers under this framework, but with the limited time today, I'm going to focus on the second last step, which is how we learn the corpus-specific models. And in particular, I'm going to talk to you about 3 specific structure mining tasks, from recognizing entities and determining their coarse-grained type, to refining these entity types into more fine-grained type semantics, to finally bridging up these entities to extract those relationships, all using different kinds of corpus-specific model learning techniques under this framework. So let's first look at how we recognize entities and determine their coarse-grained type. Again, this is a piece of review about a restaurant in Phoenix and its text. So just think about you are a person from Mars, and what you have is just a dictionary that tells you what are the food names, what are the company names, the restaurant names, and the location names in our Earth. And that's the only information you have. You have a dictionary that tells you something about on our Earth, those entity types you're interested in, and you have this text that there's nothing labeled there. So you want to go from here to there, where you have all these entity names recognized. I mean, the token spans that representing the entity mentioned in text has been extracted, and also they've been labeled with different entity types that you're interested in. For example, Purprock sandwich is a food, Phoenix a city, honor is a person. And this is a very challenging task, because think about it. The Purprock sandwich may not exist in your dictionary. That's the first thing, which means the vast majority is actually unmatchable. And second, the barbecue, it seems like under this context is obviously it's a food, but then if you are a person from Mars, so this barbecue, when you look back in the dictionary, it could be an acronym for a sort of company on our Earth. So that's the disambiguation problem that you are facing. So this is really challenging, and these are exactly the challenge our computational systems are facing when solving the task of entity recognition and cross-grain typing. But if we can do this in an automatic and high-quality way, then there will be tons of exciting applications, things just like linking this entity of different kinds to the specialized vertical engines or the applications to dig out more information about these entities. But, okay, yeah.
So your person from Mars has dictionaries that have potentially large intersections. Is that
right? So the question is whether I have an assumption that this dictionary has to have some sort of overlaps with the corpus I'm doing.
No, with each other. So like Phoenix is a city, but Phoenix is a god or a character in a movie, and pretty much every word could appear in multiple dictionaries.
Got you. So the question is whether my dictionary is also capturing this sort of synonyms or alias of different entities, like Barack Obama could be referred as just Barack, Mr. President, or some kind of other names. Yes, I assume that our dictionary has a synonym list or alias list as the subcomponent.
That's ambiguity, not synonym.
Yeah, that's a different problem. Federal is talking to it like.
So like
and maybe the name of the person, or it could be the state.
I see. Yeah. So that, I mean, that's how we. The question is whether I'm really solving the synonym discovery problem or name disambiguation problem. So what I've just described is when we just look at the resource we have, whether we have this synonym list, and I said yes, we have it, and that actually helps us to solve the problem of the entity name disambiguation, because you need to have this synonym list for different entity to generate the candidates. Let's see, if you see a Phoenix, at least you know, because Phoenix City in Arizona State has Phoenix as a synonym name. And the other Phoenix is a god, it also has Phoenix as a synonym name. So then you can generate them as the candidates to different places in the dictionary. Does that make sense? Okay, cool. So when we look back in the ways that traditional NLP method, especially the name recognition system, they're solving this NER problem. So they are having this suffering from the very extensive manual labeling process, also slow model training process. So what they do is they treat the problem as a sequence labeling problem, and they try to train a classifier for every single token in the sequences, which means they need a training data that taking the format as you have all the tokens already been labeled by the domain experts. Things like barbecue is a food, and best is all, which means it's out of the entity name boundary, and so on. So then they can train a classifier by taking the information for this particular tokens as well as the other informations for tokens surrounding this particular token you are training on. This process needs very specialized training data, and it's kind of slow because the complexity of this training algorithm. Some representative system, including Stanford NER, the Illinois NemTagger, and the IBM's language API. And starting from this, people start thinking how we can further reduce this effort. So then they go to this weak supervision system, which try to use pattern-based bootstrapping. For example, CMU's never-ending language learning, UW's know-it-all system, Stanford's deep dive, Prospere. So what they do is they ask human experts to give a list of names for particular entity types that are interesting in things like if you're for food, you have pizza, French fry, hot dog, and then they place these names back to the corpus and observe what kind of patterns actually are commonly co-occurring with these names in the corpus. Taking out those patterns, place them back to the corpus to find out more names of the same kind, and do this in an iterative way until they find out enough number of the entity names they want. But then they still need to have a substantial amount of human involvement in examining the quality of the initial set of the seed names, and also need to check in the midpoint to see whether there are some really low quality patterns or new names getting introduced into the system. So there are still lots of human effort here. And that's why we're gonna finally try to leverage distance supervision, which takes the following workflow. So they start with detecting these entity names from text like Phoenix, New York City in the first sentence, and then they try to link these names or match these names with the knowledge base entity to grab their type labels, like barbecue is a food. And you will expect a vast majority of these names actually are matchable, so I have question mark here. And that's why they further want to propose some sort of contextual bridge to propagate information from the matchable part to the unmatchable part. And in this particular example, you can see here we are using some kind of relational phrases, or to be easier to understand, it's just verb phrases start with some sort of word ending with optionally a preposition here. But then it sounds like we have a really nice mechanism to propagate things from one to the other. Does that solve all the problem? So we see two limitations of this method. The first one is when they actually predicting the type labels for those entity names, they are predicting in a context agnostic manner. So you can see these three mentions of Phoenix, and then the first and third one is referred to a bar in New York City, versus the second one is referring to the Phoenix in New York City. And then what most of the method used to do is to just assign a single label, either a location or a restaurant, to all these Phoenix that share the identical string names, and that would definitely be a very aggressive process, because you can see they're actually referring as different entity names. So that's the first problem. And second, you can see these contextual bridges, they could be in a very similar string in terms of the string name, and they are expressing very similar semantic meanings. For example, in identity, in telling you what kind of entities are happening on the left and right side, but they still are treated as two separate things. And some of the ways may be very popular, maybe mentioned 100 times in your corpus, and some other way may be very rare, like mentioned just 5 times in your corpus. And this kind of rare ways of mentioning these relationships could be kind of isolated in your propagation process. And how do you resolve these popular and rare things together in terms of their function? That's the second challenge. So my solution, the class type, I'm gonna use a gigantic graph to illustrate the idea here. It starts with a segmented text corpus where you already have the entity names and those relation phrases being detected by the text segmentation algorithms that I haven't got time to cover. And then the first thing I do differently from the existing work is that I try to model all the mentions of Phoenix separately using different individual nodes to represent them, so that we can model their type semantic based on the context in a separate way. And of course, we have this correlation between these entity mentions by just looking at how similar their contexts are. And then we still map these mentions to their name strings, because we want to propagate the type labels from these name strings through those contextual bridges, which is the relational phrase in this particular example. And most importantly, we want to group those functionally similar phrases together. So the basic idea behind here is I'm doing two data mining or machine learning tasks together. One is doing type label propagation on this gigantic graph, and second, I'm doing the node clustering or the relational phrase clustering together by looking at what they themselves looking like and what their neighbors looking like. So I'm doing these two things together, and I want to give you a little bit more detail about how we do propagation in this graph. So I'm taking the idea of smoothness assumption. So what it says is that if the graph tells you that these two nodes are very similar, let's say the weight connecting them are very large, then you want to push these two objects to have similar labels. That's the smoothness assumption. And what I mean here, to put it in the mathematical way here, let's assume Wij is representing the way that connecting these two nodes, and Fi is telling you that how likely things on the right side of these relational phrases is a location, and Fj is telling you how likely this NY node is actually a location. Then we can use this graph Laplacian term come from the NIPS paper in 2001 by the Berkins. What they say is minimizing these terms, and if you have large weight Wij, if it's forcing these square terms to be 0, and which means it's forcing Fi to be equal to Fj, which means they should have similar labels in indicating whether they are both be the location. That's the idea of the type propagation. And how we do this relation phrase clustering in a joint way. So again, think about you are just person from Mars, and these two strings are just sequence of characters that doesn't mean anything to you. The first thing you would think about is to looking at how many overlapping characters these two strings have. That's the string similarity we've been using. And the second thing is to observing how these two strings are co-occurring with other neighbors in this graph, and that's the context similarity. And most importantly, you also want to see whether these two strings are co-occurring with objects that share similar rows. In this particular case, the rows means the entity types for these nodes. And how do you know these entity types? That's when the question comes from. Why we want to do entity type propagation and the relation phrase clustering in a joint manner to help mutually enhance each other. Because once you have an initial guess on what NY is, let's say it's a location maybe, and it help you to group those relation phrases in the first round, and grouping these relation phrases consolidate these bridges and go back to polish or refine the labels for those entity mentions and do it in a back and forth way, which mutually help each other to do a better prediction. So finally, how does this class type compare with other state-of-the-art entity recognition and coarse-grained typing systems in terms of the F1 score? So what we do here is we train all the systems on the same set of documents that are automatically labeled by the distance supervision. And we evaluate all of them on a subset of the documents that are manually labeled. So we assume the evaluation data is perfect given by the domain experts. And then we are comparing with three kinds of systems. The first type is the bootstrapping. Basically, they are faced with the problem of the context agnostic prediction because they're gonna assign the same label to all the entity mentioned, share the same string name. So then they are doing this prediction on the unmatchable part in a context unaware or agnostic way. And that's the major performance gain why we can doing better than them. And the second type of method is the label propagation. So this method, they are really predicting the label in a context-aware manner, but then they do nothing to consolidate those relational phrases that share similar functions. So they will be faced with very difficult time in dealing with those very sparse relation phrases when doing the propagation, and that's why we observe major improvement over them. Finally, you will see we have this classifier that trained using very sophisticated linguistic feature like dependency parse structure, and that works really well on the general domain. But once going to those different vertical domain where the dependency parser may not be good at because they used to be trained on news article, web forum, those very grammatical clean things. But once we apply them to Yelp, to tweets, things will get worse. And you will also see that we are actually performing, all the systems performing consistently worse on the Yelp, this domain. And the reason is that because we are leveraging on these relational phrases, these verb phrases to propagate information. But for tweets, such kind of very grammatical irregular text, even there's no clean definition on what is the relation phrase there because people don't write in a very, let's say, relational ways in expressing the things between two entities. So there's still a huge space to improve for this very, irregular grammar text in defining what should be the right contextual bridges to propagate information. And that's how we do entity recognition and coarse-grained typing. And next, we want to look into how we can refine these entity types into more fine-grained semantics. Let's look at these particular examples. It's actually describing Donald Trump's this entity as it's spending some television seasons, presiding over a game show in NBC. And class type can confidently tell you that this is person by reading this piece of text. But in many downstream applications, you actually want to refine these Donald Trumps into some kind of fine-grained types that have deeper semantic than just person. And in this particular example, you can see that among politician, artists, businessmen, actually, these flagrant typing want you to look at this context and determine that he's not only a person, he's an artist, and he's actually an actor. So given this context. So the problem of flagrant entity typing is that given this type hierarchy, which is from knowledge bases or from a sort of domain experts, you want to predict a single type path in this tree that representing its type semantics. So what we want to do is we want to go from here to give a very deep understanding of the type label for the entity. That's the problem statement. And again, it's a very tough problem because once we look back at how distance supervision is assigning labels in an automatic way to generate those matchable parts, we will see many noisy labels are introduced in this process. So knowledge base tells you that Donald Trump has such entity names, and they are generally true if you don't look into a particular context. It could be a politician, artist, businessman, and so on. So distance supervision, once they look at these Donald Trumps, they will assign all the types in this blue region to every single instance or mention of the Donald Trump. And in this step, there's rather improper label being introduced. You will see author, businessman, and politician. This will be improper label or false positive label in this step. So how are we gonna solve that? Because all the prior work treating all these labels as perfect label when they're training different machine learning models. And that's where the bottleneck of their performance happen. So what we want to do is we basically want to use some sort of partial label embedding techniques to do a task called label noise reduction. So it goes from, you're given this entity dimension, I extract the features, and I'm using these features from their context as the information to denoise these entity types for this particular entity dimension. So we want to get rid of these red color entity types, which is the false positive types. And then you have clean label data to be trained using different machine learning model to get more effective classifier. And those classifier can be applied back to the on the unmatchable part of the corpus to get the whole structure out. So I want to give you a little bit more detail about how we model these clean and noisy dimensions in a separate way. So for any dimension that you don't observe any conflicting type, so basically you can assume their type labels are clean, there's no improper label. The assumption you are modeling them is pretty straightforward. It's saying you just want to rank the positive labels to be higher than those negative types. But things change for those noisy labels where you do observe these conflicting type labels. They're basically are sibling types in the given type hierarchy. So the assumption you are using to model them is say you want to rank the best, only the best candidate type to be higher than all those non-candidate types. For example, you have these all are the candidate types, actor, artist, person, author, politician, and then you have sort of way to pick the best candidate type, and you want to only enforce this best one to be ranked higher than all those non-candidate ones. And this is the different intuition when we're modeling these two kinds of entity dimension. So, but once you're using these techniques to model them together, you will have a low-dimensional vector space where things in this space, if they're close to each other, they should share similar entity type semantics. So using this space, you can do tons of very interesting things. So one thing you can do is, given a new sentence where Donald Trump is mentioned, if you extract the text features surrounding these mentions, you can then predict what type this Donald Trump mentions is. So what we do is we take down these features, we grab their embedding vector from the space, add them up together, have a low-dimensional representation for this Donald Trump mention, place it back to the semantic space, look at what is the types that are most similar to this vector representation, and it tells you it's person, politician from this candidate space. So that's how we do inferences or type prediction using this embedding space we learn. So how does this perform? We compare with systems from Google and Microsoft Research. Then those systems, they're all doing embedding using all sort of intuitions. But one thing we are many different from them is they treat all the type labels as perfect labels, but we are cleaning up those training labels to do a context-aware labeling process. So we are taking this advantage of the partial label loss function. And you can see the many performance gains come from those very flagrant entity types in level 2 and level 3. And the main insights or why does this performance matter? Because it tells us that by applying our system, we actually can perform kind of consistently well across corpus or corpora of different types, no matter what genres it's written in, its tweet, its reviews, its news article, or no matter what genres or domains they are covering on, or even it can be applied across different languages, and we have been already tried that on Arabic, Spanish, Chinese, other kinds of languages without additional human labeling effort. So now we can start trying to region up this entity of different types together to figure out what is the final structures for the whole corpus. Again, this is a piece of news article about Women's March recently, and it's text. So what we can do just now is we can figure out this entity of different types from this piece of news article. So basically, you have this Donald Trump as person, United States organization, Washington is a location. And then the task we really want to do is to figure out what is the semantic relationship between them, like Donald Trump is the president of the United States, Women's March located at Washington, D.C. But then one important point I want to deliver here is that we want to do these two subtasks together because they help each other. I mean, typing the entity and typing these relationships. Because knowing the entity types of these two endpoints actually help you confine the search space for what is the possible relations between them. And knowing the relation types between these two endpoints help you guess what is a type for those entities. So one thing I want to deliver here is want to do joint entity and relation typing. Oh, sorry. But then the prior work I'm doing is actually in a incremental pipeline way. So they detect the entity mentioned, they type the entity, and then they detect the relation mentioned between a pair of entity names, and then they type the relations. This is really a cascading pipeline, which means errors happen in any of these stages could get aggregated, cascading down the whole pipeline, and that's not what we really want to see, because we really want the entity types and relation types can help each other in doing a joint prediction. So ideas in my solutions is straightforward. I want to reduce the number of the functional blocks in this pipeline from 4 just to 2. So we're gonna jointly detect the entity names and the relation mentioned, and then we're gonna jointly type the entity and the relations as well. So I'm gonna just focus on how we do this joint typing process. So I'm showing you a gigantic graph here, and actually this graph connects to the graph that I showed in the previous task. What you can see in the bottom part here is how we can build up the interaction between the entity names to their surrounding text features, and also between these entity names to the labels that are assigned to them by the distance supervision. And that's what we already introduced in the class type and partial label embedding work. But now, in a similar flavor, you can also capture the object interaction between the relation mentioned. For example, between Barack Obama and United States in the sentence 1, you can also observe those different features co-occurring with this pair of entity names. And then you will also have labels assigned by the knowledge base, the distance supervision. Most importantly, you know the interaction between the entity name and their relation mentions. So eventually, you have this gigantic graph, and the question we ask from here is, can you have a way, a general technique that map this from this gigantic graph to the low-dimensional semantic space that can represent the entity type and the relation type in a very nice way? And the answer is yes, we're gonna have 2 embedding spaces instead of just one gigantic embedding space, because we know that the entity type semantics and relation type semantics actually exist in 2 kind of separate but correlated embedding space. There will be some sort of relations, but you want to put them in a separate way because you can see in this relation embedding space, it has text features, it has relation types, it has the relation mentioned, and things close to each other should share similar relation types. So we see here, if you have the author of as the relation type, and you have Barack Obama and Dream of My Father, that's the relation mentioned, you also have a feature like a book that exists between these 2 entity names. So they should be putting together. Versus here, this entity type embedding space, you will see Barack Obama embedded close to, in sentence 1, embedded close to politician, and you have a context word like president, something like that. So these 2 embedding spaces actually nicely represent the type semantics for entity and for relationships. But how do we get from the big graph to these two spaces. I'm going to give you a little bit more details here. The first things we need to model in that huge graph is the interaction between the entity mentioned or the relation mentioned to those features. So that's the co-occurrence, like how many times these two things are co-occur in the whole corpus. The ideas I'm using is called second-order proximity. The basic assumption is very straightforward. If you observe these two nodes share very similar neighbors in the graph, or basically similar distributions over the neighbors, then they should have similar type labels. And that's how the type from the matchable part propagate from those unmatchable part. This is the modeling of the co-occurrence between features and dimensions. And then we're gonna think about how we model the interaction between the labels and the dimensions. I mean the relation type label to the relation mention, or the entity type label to the entity mentions. Again, what we called you about the distance supervision is a very noisy labeling process. So the matchable part is very noisy, and this happens the same case for the relation mention. You see Donald Trump in the United States, once you recognize them, you map them to the knowledge base relation instance, and this relation instance in the knowledge base is actually being curated by the human experts for multiple relation types, including living, bonding, present of, and they are all true in general. But putting into a particular context, like this sentence is only present of is true. The other two are just false positive label or improper label that you want to denoise in the model process. So what we're doing here is we definitely want to do type modeling in a context-aware manner, and I'm using the techniques called partial label loss function. This loss function basically says I only want the vector representation of the relation mention to be similar to the most appropriate or the best candidate type label than to all other non-candidate type labels. For example, here in this example here, you can see this relation mentions you are only enforcing a smaller margin between this and the present of, which is the best candidate type, and you're enforcing a larger margin between these mentions and all those non-candidate types. So you are not actually ignoring those candidate types that are not the best in your objective function. And put it in the mathematical way, we are using this max margin formulation where you have the max functions to pick the best candidate types, and you have the maximum function to pick what is most likely for the non-candidate types, and you are forcing the margin between these two to realize this assumption. And the third and most important things we're going to model here is how do we capture the entity and relation interactions. We are going to use a translating embedding assumption that comes from the NIPS 13 paper from Brodis. So the translating assumption says that if you have a relation mentions Z between M1 and M2, these two entity mention, you're going to enforce this equation to always be true for their low-dimensional vector representation. And this basically says that for entity mention 1, entity mention 2, plus the relation mention should be the nearest neighbor for the other entity mention or the entity argument. And give you a very concrete example here, you have Washington, D.C. as one entity argument, plus the relation embedding, which is capital city of, should be the nearest neighbor for USA, which is the other entity argument. Okay, so that's the same case also for Paris and France. Put it in the mathematical way, we're going to use this max margin function where you have the positive relation triple come from the matchable part, and you have those negative relation triple that's doing negative sampling come from the data set you have, and then you force in a margin between these two. Yes?
So if we have Paris is in France, and it's the only Paris in France, but we have Paris, Maine, Paris, Texas, Paris, California in our corpus, does that mean that with this formula that your system is going to prefer to assign Paris to USA?
That's a great question. So yeah, the question says whether we are actually capturing the ambiguity of these names during this embedding process. The answer is yes, because remind that this is just one signals we're using to formulate the entire graph. And in this Paris, it comes from a specific sentence, and we are actually using the context feature, the feature coming from the context, to also model this Paris. So you can think about we are actually modeling the type for that particular entity underneath of these surface names. That helps you doing disambiguation together with the interaction between entities and relationships. Does that make sense to you?
We can discuss with examples.
Okay, yeah. That's great. So yeah, we can take this offline because I'm running a little bit behind the schedule. So putting all these things together, you have the joint optimization framework that can really help you reduce the errors in the sort of cascading down process. So we have the objective function where the first term modeling the entity mentioned, the second term modeling the type for the relation mentioned, and most importantly, we have the third term that capturing the interaction between the entity and the relation mentions. So minimizing this whole formula gonna give you the predictive power for predicting both entity types and relation types in a joint manner. And we have this performance comparison with many existing relation extraction systems, including a system come from MSR, come from UW, come from Stanford. But the major insight behind this comparison is that we not only do a joint modeling of entity and relation, but we also design this partial label loss function to denoise the matchable part, which both of these things hasn't been considered in all these state-of-the-art relation extraction systems. And so that's where the major performance can come from. And why does this matter? I mean, why does this matter that we can do a joint predicting of the types of entity and relationships across different domains? So here I want to give you a concrete example on how we are applying this co-type technique to really benefit the life scientist. So what we do is in a partnership with UCLA Medical School Mayo Clinic and USC Genomic Institute, we want to turn the entire PubMed paper, which is 20 million PubMed paper of the abstract and paper content, into a gigantic structured network, a knowledge network, that you have different biomedical entities connect to each other, disease, gene, drug, protein, pathway. And what we can do, the first thing we can do is we provide the user an interface to engage with this network. And that means you can input any two entity types, let's say a specific heart disease type and a gene, and we're gonna visualize you a subnetwork between this heart disease and these genes. And then we're gonna provide you the function to explore this network by just clicking on any of these structures. We can give you a ranked list of paper that most relevant to this. And this changed the whole game that people explore the literature by typing a couple of keywords. Now you can just dive into very particular, very concrete facts that you are interested in to explore the life science literature, which largely reduce the efforts when you're reading the paper, in doing the raw research. And the most impressive part is how efficient we could be when compared with domain experts' effort. So bioinfo network is a totally human curated network about protein-protein interactions, 94 kinds of protein-protein interactions. And it took human more than 2,500 man-hours to just annotate 1,000 sentences for around 2,700 facts. That's what human can do in their best because they're finding the best domain experts. And what we can do here is using the Effort-Light StructMine to build up this knife net, which is turning 4 million PubMed papers into a structured network with 1,000 different entity types, which is the node types, and then 400 different relation types, which is the edge types. And we can do this really within 1 hour on a single machine. And the most impressive part is we can get tons more facts than what human can do in a limited time. And we can get tens of thousands times more relationships compared to bioinfo network with acceptable accuracy, which is around 62 something for classifying these different relation types into classifying these edges into 400 relation types. So there's still huge space to improve here, to look into how we can take more signals to build up a more accurate network. But it's really exciting to see these things happen without human effort. So what I just talked about is how we can turn a particular corpus into a structured network by solving 3 structured mining tasks step by step using this idea of Effort-Light StructMine. And I want to summarize my contribution in this work. So I propose an innovative framework called Effort-Light StructMine that can really accurately model the noise in the matchable part when we're doing the expansion from matchable to unmatchable to really get the structure for the whole corpus, and which means we don't need any corpus-specific labeling in this whole process, and it can work for corpus from different domains, different genre, written in different languages. And then I apply this Effort-Light StructMine to 3 specific structural mining tasks, from recognizing entity, determining the cross-gram type, to refine the types into more fiber and semantic, to finally bridging up the entities to build up the whole structure. and the techniques I've been developed has been transferred to different institutes and companies. Most importantly is I present a way that we can have a game-changing idea to really manage, explore, and analyze big text data. That is, first turning this massive corpus you are interested in, the data sets you are interested in, into a sort of structured network to capture their factual knowledge. And then you can apply tons of data mining and machine learning techniques that used to work very well on this structured network to turn this network into knowledge or gain insights. And at the end of the day, you have a very effective way to mine knowledge and insights from different kinds of text corpus. So looking forward, what will be the next big things? We have a nice way to turn corpus into structured network. And I want to tell you a little bit more about my vision in turning this network into knowledge. So you can see we have an example of turning the life science literature into a sort of structured network. And then we can build out different analytic and exploration functions to help life scientists. And same things can happen for other sciences and engineering disciplines. So the vision here under this slide is that we have a nice way to turn literature into structured network. And the next big thing is about how you mine this network, how you use and analyze this network to really help scientific research. And just give you an example here. You have a nice network capturing the life science knowledge from the PubMed papers. Can you predict the missing relationship between these nodes in this gigantic network, like giving some scientific hypothesis about whether this disease will also associate with that genes that you never observe when you're just reading in a very narrow scope during your daily research? Let's say these kind of insights can come from papers that talking about animals' genes. But if you are a cancer expert, you're just reading on your narrow area that about humans' cancer disease and their genes. So this, by modeling the entire literature, definitely can do something different from how the life science research do every day. And this can be just switched from life science to any other domains, including computer science, physics, chemistry, and so on. And second, since our human behavior and our preferences, our interests has been captured. This such rich information have been captured in our user-generated content, things like social media posts, the reviews that we write, the chatting, the dialogues that we talk to our chatbots, or any sort of other computer systems. All these user-generated contents now can be transformed into a structured networks that you're representing the knowledge there. And we can further combine this structure with sort of other structured behavior data, like our social network links and our transaction records, or even our electronic health record, these kind of things. And you have a way to do data integration, combining these two together, you really have a unified representation of humans' behavior, interests, and preferences. So the next big thing is about how to use these unified structures to really benefit our intelligence systems, to make them more personalized. And this including how you use this chatting history with your medical chatbot and those health discussion forum posts to really turn into structure to build out more personalized medical chatbots. And finally, the third big thing is how we engage with our physical world by really building the sensor signals, which is structure, with the related text signals, and to help the smart city applications in building better cyber-physical systems. And I can talk more about this offline for you as well. So I really want to thank all my collaborators from academia and industry and my funding agencies. And this will be the end of my talk. I'm really happy to have you here attending my talk. I would like to take more questions now. Thank you. Yes.
So could you go back to the slide where you compared to the different network embeddings like deep walk?
I see. You mean this one?
Yes. So I'm wondering, so the network you compared to, they were designed for a different purpose. The assumption was that the network is given to you. You're not constructing the network, then you're trying to do something. In your case, it seems like you construct the network and then you try to do something. So I'm wondering if these results, maybe that your algorithm is actually, sort of designed for the kind of network you are constructing, because I don't see a comparison to, other knowledge graph embeddings like Transi.
Got you.
So I'm wondering if you compared to those and suited to,
That-
rather than the
okay.
homogeneous network embedding.
Okay, so the question is whether I'm comparing with the right kind of methods, including the knowledge graph embedding those vast number of literature. So the answer is yes and no, because first, the methods I compare here, most of them already compare with the knowledge graph embedding in terms of the techniques. I'm not mean in terms of the task they are solving, because knowledge graph embedding, when they are evaluating on different applications, they mainly evaluate on whether they can complete the knowledge graph in adding up more facts to the existing knowledge graph in a more accurate way. And these embedding methods, when compared with them in their own papers, they are just evaluated on, let's say, whether we can do better document classification, all sort of things, because they only use the idea of turning any general graph into a low-dimensional vector representation. So in terms of that, we are also doing the same thing. We are comparing all these methods not on a specific task, but just seeing whether these embedding methods can model a graph structure in a very nice manner to capture their semantic just using the graph structures. And in that case, you can see we compare with multi-R, which is specifically designed for relation extraction. This one is also a specific design for relation extraction, but deep work and lie is not designed for any information extraction task, but it's designed for modeling the co-occurring interactions or any label assignment interactions between documents, word, features, and so on. So we should also compare with them to see whether the model we design have a better predictive power in terms of modeling any general graph. Does that answer your question?
Sort of,
Yeah. Yeah.
So you compared the LifeNet and the BioNet, like, and you looked at the accuracy. Did you look at the false positive rate, like how many false positives are being given?
Yeah, so the question is whether I also evaluate using other evaluation metrics, including F1 or basically different possibility. Yes, that's a good question. So actually, the false positive rate is also comparable. So I think you are concerning about whether I have lots of negative examples. But since the data sets I'm evaluating on, I make sure that we have very balanced different categories. So it won't, even using the accuracy, it won't be kind of biased towards those negative examples. But definitely, I can show you more results on F1 scores or also other metrics to make the comparison more comprehensive. Yes.
So specifically this again, if you're looking at 4 million PubMed papers, is that full text or is that?
That's a good question. So the percentage of the PubMed papers have full text is around 20% or even less. So that's also the percentage that we are using here. Among these 4 millions, only 20% sort of something have full text. Other are just abstracts. And a small portion of things that I haven't included here is we're also using different texts about a disease, all sort of biomedical entities from the health portals, including Wikipedia, those Mayo Clinic's websites.
So I think that's actually a really interesting point, because you didn't talk very much about how you extract the information from existing knowledge bases. I would very much like to understand
Okay.
how you formulate that, because clearly there's a large number of different databases.
Yeah, I can talk a little bit here. So the question is whether I'm really taking advantage of existing knowledge about biomedical entity. And the answer is yes, because we are using distance supervision. And what does that mean is that take the overlap between all the knowledge bases you have about biomedical entities. For example, UMLS, MeSH ontologies, gene ontology, disease ontology, there's all sort of things we already have there. I try to get the overlap between those and the corpus, 4 million PubMed paper I have. So that's representing the existing knowledge, but that's very sparse. And we do the expansion to the entire remaining part matchable of the PubMed papers. And that gives us a much larger graph than what those knowledge base has. So I can show you some concrete statistics from our demo paper in the ACL that give you a table about telling what is the existing number of facts, entities, or relationships we got by taking the overlaps. What is the resulting number of facts we got by using my methods? Yeah. Yes.
So taking sort of the reverse of what Ellie just asked, when you make a
That's good.
vector, and how well can we explain how that number originated? How can we track it back to particular corpus, particular training material, so to speak, that ended up influencing that number?
That's a great question. So the question is whether we have a way that we can first quantify the confidence of these facts. Second, trace back to the support evidence or the places that we extracted. So for the first question, it's a very great question that we are currently also thinking how to overcome. Because by our method, you do have a confidence scores quantify how likely this fact is true from that particular context. But we are not tolerating to store all the facts that we extracted if we set up a very low threshold, because there would be just exponential number of facts that we can get. So our computational system cannot tolerate that. So we set up a kind of restrict threshold, let's say 0.9 may be the case. That's also the case for most of existing systems like NEL and the OpenIE system, to really store in the knowledge-based systems, which means we discard the vast majority of our facts. We can also extract it. And an interesting future question is how you design an open world knowledge-based systems, database system to really store all these things together. And then for second question, yes, we also index where these facts come from by just giving the specific sentence ID, document ID to that fact. So you can trace back to the original corpus to see where it's from. Yeah. Yes, Patrick.
If I understood correctly, so you require that you are able to tag your unknown corpus in such a way that the distance between entities is relatively small, because then the context words are the relation words.
So the okay.
And so is this true? And is it always possible to do that when you have so unknown?
So yeah, I first need to understand the question clearly. So when you say the distance between the entities and relations, can you elaborate more on that?
So if I have a corpus and I label some words as entities, you want the context between the two entities to be relatively short. If it's too many words between them,
I see.
that would sort of mess up everything.
That's a great question. So the question is basically asking what is the context window that I'm using in our framework. So I'm basically just consider each sentence separately, which means things co-occur within a sentence. I will try to see whether there some sort of relationship happen. But then for the long distance relationship, like across multiple sentences, that's something we need to leverage the knowledge-based embedding to predict them by the. So basically, we are doing more on explicit relation mentions instead of implicit relation mentions that are mostly happening in biomedical entity, in biomedical domain. Things could be related without very long distance. Yeah.
So to put it in a specific English language context, you're not solving the relative pronoun problem.
You're right. So let's say what you ask is basically a co-reference resolution problem. Yeah, I'm not solving that problem. First of all, in my systems, pronoun is actually kind of we didn't consider it when we do this like relation extraction, because it's not a name entity in that sense. So the next step is first synonym discovery, resolve things that are synonym to each other. Second, co-reference resolution to put in those pronouns back to their right entity names. So there's still tons of things need to do from these steps, but I have some existing work in doing those, but I didn't get time to cover in this talk.
Last question. I was looking at the results that you first showed, the first paper, the first work, the contribution. You had a very large increase on Yelp, more than any of the others. So I'm wondering why is that? Like you had a very, for some of the others it was 10%, and other people also not doing too much, I think, like 5%. With Twitter, it's a bigger improvement. But with Yelp, we see everyone getting 20s and there's just one system with early 50s and you got early 80s. So I'm trying to is there some kind of overfitting, or what do you think happened?
So yeah, the question is asking why we have such huge improvement compared to the other two domains. I mean, on the Yelp, and the reason is basically what I just explained. Why we are doing better than those systems. First, These systems, one major kind of system, they actually predicting the same type label for all the entities share the same names. And this is extremely aggressive for customer reviews because we're talking about really different entities, but they share similar names, like a Phoenix I just talked about. It could be a city or could be a restaurant. And these cases happen a lot in the Yelp compared to other domains. So which means if we don't solve that question, that problem, those systems basically will not be very applicable on those domains. And also, that's the same when people mentioning the relation phrases in a wide range of different ways. That also happens a lot on Yelp compared to, say, news articles. By grouping those functionally similar things together really benefits the performance, which the existing world doesn't consider that. Thank you.